Hello, I am Emrah Karagöz. I will be presenting RSA and timing fault attacks. Before starting the presentation, I want to give square and multiply algorithm to compute m to the d mod n. Okay, if we have the binary representation of d, d0, d1 to dn minus 1, we start with setting z is 1 and c is m. And in each step from 0 to n minus 1, if the di bit is 1, we multiply c with z in modulo n and update the c as the new value. And we always square the z. In the final, we return the value of c, which equals to m to the mod n. There is an example on the right to check the computations. RSA crypto system generating keys. First, choose two primes p and q. In the second, set n equals to p times q, and phi of n is p minus 1 times q minus 1. We then choose d and e such that e times d equals to 1 in modulo phi n. Now the secret key becomes p, q, and d, and the public key becomes e and n. Note that x to the ed equals to x modulo n by Euler theorem. And also note that to make the verification easy, e is mostly chosen as 3 or 2 to the 16 plus 1. On the right, I gave a code to generate primes, m-bit primes p and q, and the secret key d. RSA crypto system, decryption, or the signature. Both RSA decryption and signature algorithms requires the secret key d. The decryption can be performed for a given ciphertext c. The message becomes m equals to c to the d mod n. The signature can be performed as, for a given message m, the signature is c equals to m to the d mod n. The code on the right is just to illustrate, gives the how we sign the message m by using the secret key. RSA crypto system, encryption or verifying. Both RSA encryption or signature algorithms, the verify algorithms, requires the public key e. In the encryption, for a given message m, the ciphertext becomes c equals to m to the e mod n. In the verification, for a given signature c, we verify the signature by computing m is equals to c to the e mod n. If so, the signature is valid, otherwise it's false. The code on the right is a verifying code for a given c and m by using the public key e, which is 2 to the 16 plus 1 in this case. RSA implementation benchmarks. The RSA depends on the size of n, which is the product of p and q. The size of n becomes 512, 1024, 2048, or 4096. And the generating keys takes longer if the size of n gets bigger. Decryption is faster than the generating keys, but it also gets slower when the size of n grows. Encryption or verify should be very easy. That's why e is fixed to a small number to make this encryption or verification very easy. So it's the fastest one. It's very fast comparing to generating keys or decryption. Note that key generation takes time because the primes are validated with error probability 2 to the negative 80. However, it's done once. Timing attack. This is a type of attack on the square and multiply algorithm. If you are given the binary representation of D, remember that in the second step, if di is 1, we perform a modular multiplication. And in 2b, we always perform squaring for each bit. In this attack, the attacker asks for signatures on a large number of random messages, M1, M2, Mk, and measures the time Ti for each signature Mi. The attacker then computes the time Tij for the jth step in square and multiply algorithm, which varies depending on Mi. And the last step, the attacker used the correlation of Tij and Ti to guess the bit J of secret key D. For example, let's say D0 is 1. In the second step, which is E equals to 1, C is M and Z is M square. If D1 is 1, the signature time T includes the time small t for C times Z, which is M times M squared in modulo N. Otherwise, it doesn't include. Therefore, T times T correlates with capital T. How varies? Simpler modular multiplication or modular squaring varies depending on the size of M, because it's easy to multiply small size m's, and it depends on use of modular reduction. If the multiplication of m1 and m2 is less than n, no need for a modular reduction. Also, it depends on number of multiplications, squarings, or modular reductions. For example, when computing m1 to the d modulo n and m2 to the n d modulo n, for m1, 86 bits of m1 and 86 of m2, their sizes are same. D is 256 bits and n is 256-bit number. Takes 113 multiplications and 256 squarings for both, but takes 111 plus 255 modular reductions for M1, but 112 plus 255 modular reductions for M2, which is we use one more modular reduction for M2. Horseshare's perspective. One can find suitable m's such that a specific modular multiplication, C times Z modulo n, is extremely slow. If the total time is ever fast, it means slow time for C times Z doesn't contribute to the total time. Therefore, di is 0. Otherwise, di is 1. It helps us to recognize the time difference. Timing attack, software versus hardware implementations. Actually, it differs in software implementations or hardware implementations. In software implementations, timing attack gives a bit accuracy because there are many other operations running on CPU. Also, varying time differences because there are many overheads and CPU power is so high. But on the hardware implementations, it gives us a better accuracy because hardware is just programmed to perform the algorithm, and it gives us a better time differences because of better accuracy and limited CPU power. Timing attack arm trick 1. We modified the square multiply algorithm in RSA signature so that modular multiplication at ith step is extremely slow. As you see in the code, and it's also shown, if I is the bit flag we are looking for, it multiplies very slowly. Of course, this is performed when the DI bit is 1. So it becomes very easy to recognize the time difference on the total time. R trick 2, we choose M whether it takes time in modular reduction. As shown in the code, if A times B is less than N, there is no need for modular reduction. Otherwise, we should apply division many times to find the same remainder. So it slows very significantly. Example attack. We choose the following parameters: P of a 128 bits, Q 128 bits, D 256 bits, and N as the product of P and Q, it's a 256 bits. Don't forget the size of N, it's 256. Example attack on bit 1. If D1 is 1, it should compute C times Z, which is M times M squared modulo N. We choose two sets of M's, M1s and M2s, so that the cube of M1 is less than N, so it doesn't use slow modular reduction, and M2, the square of M2 is less than N, but the cube of M2 is greater than N. So it uses slow modular reduction. We choose a set of M1s such that M1 cube is less than N. So since the size of N is 256, we randomly choose messages of 85 bit size. For the M2, to satisfy the inequality, we choose 86 bits messages. For these two sets of M's, M1s and M2s, we compute the total signature time and print the results. If they are close to each other, it means D1 is 0. Otherwise, D1 is 1. When we compare the results on the right, they are very close to each other. So D1 is 0. And as we check the actual value of D1, it matches. If it were 1, D1 is, if D1 were 1, we would have the following timing results. As you see from the table, they differ a lot. Example attack on bit 2. Now, if D2 is 1, it should compute C times Z, which is M times M to the 4th in modulo N. We choose two sets of M's so that M1 to the 5th is less than N, so it doesn't use modular reduction. And m2 to the fourth is less than n, but m2 to the fifth is greater than n. So it uses slow modular reduction. For this purpose, we choose m's of size 51 bits to satisfy the given inequality. For m2, we choose 52 bits messages to satisfy the given inequality. For these two sets of m's, we compute total signature time and print the results. If they are close, it means D2 is 0, otherwise D2 is 1. When we see the results on the right, we see that they are actually close to each other, so D2 is 0, and we are correct. If D2 is 1, if D2 were 1, we would have the following results which are not close to each other. Example I take on bit 3. Now, if D3 is 1, we should compute C times Z, which is m times n to the 8 in modulo n. We again choose two sets of m's so that m1 to the 9 is less than n, so it doesn't use the modular reduction, and m2 to the 8 is less than n, but m2 to the 9 is greater than n, so it uses a slower modular reduction. For this purpose, we choose m1's messages of size 28 bits for m1 to satisfy the given inequality. For m2, we choose a set of messages of size 30 bits, so it satisfies the inequality. Note that 256 divided by 9 is 28, so that's why we differ the size of m1 and m2 with respect to that number. When we compare the total signature time for these two sets of m's, we see that they are not close. The timing results were given on the right, and we see that they are not close. So D3 is 1, and this is actually correct. C is now updated to n to the 9 modulo n. Example I take on bit 4. If D4 is 1, you should compute C times Z, which is m to the 9 times m to the 16 modulo n. We again choose two sets of m's so that m1 to the 25 is less than n, so it doesn't use the slow modular reduction, and m2 to the 16 is less than to the n, but m2 to the 25 is greater than n, so it uses slow modular reduction. For this purpose, we choose 10 messages of 10 bits for m1 and 12 bits messages for m2. Note that 256 divided by 25 is around 10, so that's why we choose 10 and 12 to differ m1 and m2. And from the results in the bottom, we see that timing results differ a lot. So they are not close, which means D4 is 1, and we are correct. Example I take on bit 5. Similar ways to choose m's, and when we compare the results, we get close timing results, so D5 is 0, and this is correct. So, can we say our attack is successful? Our tricks works up to some j bit. In our case, it's actually it's j equals to 5 with 100% success. For bigger cases, it's not so easy to find suitable m's. Notice that the probability of m is less than n, but m squared is greater than n is actually 1 minus 2 to the negative log m over 2. Therefore, for any m less than n, it's possible to exceed n for higher powers. Fault attack. This is a type of attack on Chinese remainder theorem to compute n to the n d mod n. dp is m to the dp mod p, where dp is d mod p minus 1. And similarly, cq is m to the dq mod q, where dq is d in modulo q minus 1. So the actual ciphertext C is T1 times Cp plus T2 times Cq, where T1 is 1 in modulo P, but 0 in modulo Q, and T2 is 0 in modulo P, but 1 in modulo Q. In this attack, assume Cp is correct, but Cq is not. So there is a fault on Cq. Then C prime, the naive C, becomes T1 times Cp plus T2 times Cq prime, the faulted Cq. As a result, the JCD of C prime to the E minus M and the modulo N gives a non-trivial factor of N. For this attack, I didn't do a simulation because it's very easy to perform. Thank you for listening to this presentation.